All right, let's write our differential equation again. It was dq dt. That was the current, the rate of change. And we're going to combine those fractions we had and write it this way, minus q minus the EMF times c over RC. We had the EMF over R by itself, but to get a common denominator, we want to do it that way. And we made it where there's a negative sign in front of the whole thing. Okay, so you look at that, and the easiest differential equations are solved just by integrating them. Right? So we could integrate this side with respect to time, this side with respect to time, but we can't really do that. Right? The integral of dq dt with respect to time would just be q. But we can't integrate this with respect to time because it's got the function we're looking for in it. This is why differential equations are hard. Okay, so in this one, we just have a little trick. All we got to do is break this thing up and treat it as two different differentials. So we're going to bring this under here, and we're going to put this up here and see what we get. Then we have dq over q minus the EMF times the capacitance equals minus, this goes up there, dt over RC. Okay? So now instead of integrating the whole thing with respect to time, we'll just integrate both sides based on a similar sort of set of conditions. Okay? So we're going to integrate the left with respect to charge, dq. And we're going to integrate the right with respect to time, dt. And what this shows is that we now need limits for this integration. Okay? So we only solve this for specific cases. If this circuit is changing in time, we need to know something about how it started. Okay? So usually then, you'll see this circuit drawn with a switch. And you can use the switch to define when you started and in what condition it was when you started. Sometimes there's a switch that goes to two places and one goes to ground, and I won't make it that complicated. Let's just keep it simple like this. So let's look at it and say we close the switch at time equals 0. And let's say then that while the switch is open, everything's discharged. There's no charge on the capacitor. Okay? So the charge at time 0 is also 0. So you can also say Q equals 0 at time equals 0. So we can write the limits on our integrals to be the same for both integrals. So we're going to integrate from time 0 up to some time t. Okay? It's a little confusing that I use the same t here as here. Sometimes people put primes on them, but let's just try to keep it simple. We're integrating this integral from time 0 to time t. We're integrating this one saying at time 0, the charge was 0. Right? This has to be an amount of charge. And at time t, it's going to build up to some charge, which we'll go ahead and call big Q, even though we called it big Q down here. It's going to be the same thing. Okay? So these are the integrals we have to do. Okay, so the integral of dq over q minus a constant is just the natural log. You know, the integral of dx over x is natural log x. If you have this constant hanging here, you just stick it in there. So this one is natural log of q minus the EMF times the capacitance evaluated from 0 to q. Okay? And the integral of dt with respect to time is just t. So this one is minus t over RC. Minus t over RC evaluated from 0 to t. All right. Let's see. So now let's figure out then what we got here. So this, now we're plugging q into the variable q. When we're plugging t into the variable t, this becomes natural log of q minus epsilon, or minus the EMF times c, minus the natural log, we plug in 0, of just minus the EMF times the capacitance. So that's just a log, or natural log minus natural log. And then here, minus we plug in the t for the t, we get minus t over RC, minus when we plug in 0, we get nothing. So two natural log terms, and then equals minus t over RC. Let's keep going.